All right, we are going to start the next topic. The next topic is shear diagrams. So the first problem, this is our example. Again, as I said, this is about beams. And we have a beam here, we have a hinge on the left end, a roller in the middle, 10 kip load at the end. And the problem here will be to find the reactions and draw the shear diagram. And again, I'm not going to dwell on the reactions because you can all do those at this point. And what we're going to find, here's my free body diagram. And again, I'm going to take the AX is 0. We can find AY and BY using those equations. You can pause the video and look at those equations. And we end up with, this is the reaction at A, this is the reaction at B. I have a 10 kip load. Now if you look at this problem, you'll notice that it looks like a diving board, right? There's somebody standing at the end, essentially. And this is the roller in the middle of the diving board, if you've seen a real diving board. And the hinge at the end. And what do we know about the way diving boards deflect? Well, what do we see? We see that, you know, when somebody stands on the end of the diving board, what happens to the diving board? It goes up in this region and it goes down in that region. So what I want to emphasize, is that when we draw our free body diagram, what we are showing is what the supports do to the diving board. In other words, this is the diving board and the support at B pushes up with 20 kips. The support at A basically pulls down 10 kips, which makes sense. In other words, you have, when I look at this diving board deformation, I can see at this point, well, we're pulling down that. If we don't hold that down, we can see that what's going to happen is this point's going to go upward. The point will go upward if we don't hold it down. So we have to remember that when we get our final free body diagram, we are seeing what the supports do to our beam. In this case, our beam is a diving board. Now, what does that mean if you're building a diving board? What do you have to do here? You have to anchor this support, don't you? Because if you don't anchor it, it's going to be pulled up. So just as get an understanding of what these mean. These mean I have to create a support that can pull down. That support has got to pull down that beam. It's got to hold that beam down. So that's what it's doing to the beam. And then this is the deformation. So let's start with that. That's what the meanings of the reactions are. And in this case, this is the diving board deformations. Okay. I want a little bit of a review here before we go into the shear diagram. And I want to really emphasize the rules. And so there's a little bit of a review of statics again, but you know we'll get there. But I'm going through it for a reason. The rules when we draw free body diagrams. And let's start with a truss, okay? And what are the rules when we draw a free body diagram when we're analyzing a truss? We have to remember that a truss consists of long, skinny members that are connected with hinges. So, in other words, there's a hinge there, there's a hinge there, there's a hinge there, and then these members are long and skinny. And if you remember all the problems that you did in your statics class on trusses, the forces on the truss were always at the nodes. They were always at the nodes. We never put a force there in the middle of the member. Well, why didn't we do that? We didn't do that because it's a long, skinny member. If I start putting a force in the middle of a long, skinny member, what's going to happen? It's going to buckle that member. In other words, that member can't take it. It's going to collapse it. So, a true truss, and yeah, this is a little bit theoretical, but this is, if we're talking about a true truss, we never ever put a load in the middle of a member. And the reason why is that, like I say, truss members are long, skinny members. Now, what does that mean for us? That means that truss member can take tension, it can take compression, and that's it. Okay? Nothing else. It can't take any other, well, we'll talk about it. It's not a beam. And when it can take only tension or compression, if I come in and here's my truss and I want to analyze, create a free body diagram and analyze that particular point D, what does that mean? Well, I follow the rules. I come in here, I make my, create my free body diagram, and I make a loop, a closed loop, and wherever I make cuts, I have to put a force or forces. So I've made a cut there, I made a cut there, I made a cut there, I have to, and so when I draw my free body diagram, I draw exactly what's in that loop, and then I put a force or forces where I made the cut. So I've got that, I've got that, I've got that, I've got that. So that's that. Okay, and then I made my cut, so I put a force there, I put a force there, and I put a force there. And like I say, since my truss member is long and skinny, it can only take tension or compression, and that means that tension or compression is right along the axis of that member. So I put in my forces like that. Now, if you remember the way that our free body diagrams work is that if this arrow goes away from the body, which it does, so in other words, my body, this is the body right there. That's my little structure. And I've cut, that's the structure. If the arrow goes away from the body, then we are showing tension or pulling the body. Okay? If we show an arrow going toward the body, then that is compression. In other words, pushing. So tension or compression. If it's pushing, it's compression. If it's pulling, it's tension. Because when we pull things, they go into tension. If we push things, they go into compression. So now, the way traditionally that we solve truss problems is that we always show tension. So in other words, we always show the arrows. It's just a convention. We don't have to do it this way, but this is the way everybody does it. We show the arrows going away from the body. When they go away from the body, that is tension because it's pulling, and it's pulling the body, not pushing the body. And then
remember, we can do that because it's a letter. I could show tension or compression. I could show toward the body or away from the body, but the way everybody does it is showing it away from the body. And then when we get all done, if we solve for F sub ED, for instance, and get a negative number, what does that mean? I turn the arrow around and point it to the body, and that means that the member ED is in compression. If we end up with a positive number for FCD, then that means that our arrow is correct, and that member CD is in tension. That's the traditional way we do it. Now, so that's how we analyze trusses. Okay, now, the reason I'm talking about trusses to a certain extent is that we can make a beam out of a truss, and this is what we frequently do. So in other words, I make this structure here with these long skinny members, and then we make it in such a way that it's shaped like a beam, ultimately. And we can create our diving board with this truss. We put the load there. So now we have a truss, we have a beam that is made out of a truss, and why do we do that? Well, we do it because we now have a very light beam. There's a lot of air there, and it's very lightweight, and it ends up to be strong for its weight compared to its weight, and so that's just a typical thing that we do. Is we make in other words, rather than use a solid beam like this, we make the beam out of a truss. Okay. Now, let's look at another situation in statics, and that is the cable. How did we analyze cable problems? Well, the first thing that we know is that cables can only take tension, right? We know that because if you try to put compression in a cable, it deforms. It can't resist compression. A cable cannot resist compression. A truss member is stiff in both directions. It can take both tension and compression. But a cable can only take tension, which means that when we draw our free body diagrams for a cable problem, we're going to show tension again. So let's look at this as the simplest of cable problems. I've got a little pulley here, and I've got a cable that goes around and it supports a weight. I analyze this by making this free body diagram here, and I take a free body diagram of the weight. So I have the weight is going down, and we made a cut through that cable, so the tension, again, is going away from the body. In this case, it's going up. And so, again, the tension is drawn away from the body. Well, now, we also remember, what about this cable? Now, if I compute this tension, and what do we know about that? Well, that tension is the same everywhere in this cable. If it's one continuous cable, that tension is the same everywhere. So I only have to find it in one location. If I know the tension right here, well, then I know the tension right there. The same thing to a certain extent, well, same thing with the trusses. If I find the force in the truss, I say it's tension for the sake of discussion. If this is the tension in the truss member, we find it right there. Well, the tension there is the same as the tension there is the same as the tension there is the same. That's one of the assumptions. And so we only need one number for that truss member. That is the tension or the compression in that truss member. It's the same everywhere. Cable's the same everywhere. And then, as we talked about, when we have a roller, we have a Y force only. We've gone through that. So these are the rules of statics. And when we cut different members and different supports, when we have a pin, we have the X and Y forces. Okay, but now what we're doing is beams. And when we cut a beam, what do we have? We have an X force, we have a Y force, and we have a moment. Why do we have a moment? Because beams, let's discuss it. Beams can resist bending. In other words, if I look at my beam here, notice I have a force that is perpendicular to the axis of that beam. Well, I can do that because a beam is basically a short fat member as opposed to a long skinny member. So, in other words, I can't put a force perpendicular to the axis of my truss member because it's long and skinny. It can't resist it. It can't resist bending. A truss member cannot resist bending. A beam can resist bending, and the reason that it can resist bending is that it's basically short and fat and not long and skinny. So that's, in a sense, the definition of a beam, is that it's a member that can resist forces perpendicular to its axis. A truss member cannot resist forces perpendicular to its axis. So that means the beam can handle bending, which means that it has a moment, an M component. And so when we look at a beam, we're going to have an X force, a Y force, and a moment. And we're going to give those the symbols: the X force, for instance, the N, the Y force, V, and the moment, M. So what does that mean? That means when I cut a beam, I'm going to have a V, N, and M. So we're going to get to this, but we're going to have a V, N, and M when I cut my beam. So that is the logic behind it, and it's because the beam is fat, can handle this. Okay, so let's get back to our diving board problem. So here's our diving board problem. Looks like that. And we know that it's going to deform like that, and we're going to set up a coordinate system. So on the right side, the left side is going, for the rest of this course, the x equals 0 will be at the far left end. So we want to be on the same page. I don't want to have coordinate systems going all over the place. So x equals 0 is always at the far left end of the beam. So stick with that. We will always use that x. So whenever we have an x in any of our equations, the x equals 0 would be at the far left end of the beam. So what we're going to do is we're going to look at this beam problem, and I'm going to make several cuts in this beam to analyze it. And I'm going to make a cut at 2 feet. So in other words, I'm going to cut here. I'm going to make a cut at 4 feet. Oops. At 4 feet. So I'm going to make a cut over here. And I'm going to make a cut at 7 feet. So it's going to make a cut over here. We'll analyze each of these problems. So cut 1, cut 2, cut 3. Let's start with cut 1. I'm going to make, so here's my final free body diagram. I've got the 10 kip load, I've got the 20 kip reaction, I've got the 10 kip reaction. So there's my final free body diagram. And what I'm going to do once I've created that free body diagram, which you can all do now, is I'm now going to make a cut here. And then in this particular case, I'm going to look at the right side and I'm going to create that free body diagram there. So that free body diagram is this over here. So again, wherever we make cuts, we have to put a force or forces. So I made a cut there, and since it's a beam, the rule for making a cut through a beam is I have to show a V, an N, and an M. In other words, a vertical, a horizontal, and a moment. So I have this this free body diagram here. Oops. So there is my free body diagram, just to be correct. And what I'm going to do is I'm going to take moments about that point C? Well, first I'm going to start with the sum of the forces in the x direction, as we always do, which is sum of the forces in the x direction. What do I see? N equals 0. So that's what's going to be the case for pretty much all semester. I'm going to take the sum of the forces in the y direction equals 0. And what do I see? I have what? I have that 10 is going down, that v is going down, and as I said, we set a sign convention for this equation only, and I'm choosing upward positive. So what do I see? I have that's down, so it's minus 10. That's down, so it's minus v. So minus 10 minus v. I get v is equal to negative 10 kips. Now I'm going to take moments about point C. So there's my point C. Well, v goes through it, n goes through it. So I don't need to consider points. I don't need to consider v and n, but I do need to consider the 10 kips and the moment. And so what do I get when I look at that free body diagram? Again, I'm taking clockwise being positive, and I end up with negative 10 times 2, and then that's also counterclockwise, minus m equals 0. And I get m is equal to negative 20 kip feet. Okay, so that's my cut number 1. Now I'm going to do cut number 2. So I'm making my cut over here at a distance of 4 feet. And here's my beam. I've got my V, my N, my M, as we're going to do over and over again, the V, N, and M. And again, I'm going to take the sum of the forces in the y direction equals 0, and I end up with the same result. I get V is equal to negative 10 kips. And then I'm going to take moments about point D. So now I've got what? Now I've got my force times distance is 10 times 4. And my M, again, is counterclockwise, so it's negative M. And of course, it's negative 10 times 4 because that's counterclockwise also. So now I solve this for M. I get M is equal to negative 40 kip feet. So let's make a little list here. I'm going to have my X, my V, and my M here. And I'm going to so for my different X values, so what we're finding is that my first cut was at 2 feet. My second cut was at 4 feet. So that's at x equals 2, x equals 4. So x equals 2, x equals 4. Let's fill in our values. My v is negative 10. My v is negative 10. My m is negative 20. My m is negative 40. So we can start to see a pattern here without having to make all these cuts. So in other words, my v value, you can see it doesn't matter whether I make a cut here, wherever before I hit that roller, so I can make cuts all through here. It doesn't matter. I'm going to get the same type of free body diagram. It's always going to be looking like this, and in the sense that if I take the sum of the forces in the y direction, I'm going to keep on getting the same result. I'm going to get negative 10. So by logic, I can figure out that, even when x is 0.0001, I'm going to get negative 10. At 1, I get negative 10. At 2, I get negative 10. At 3, I get negative 10. At 4, I get negative 10. At 4.99999, I still get negative 10 because I'm not quite to the roller. The roller's at 5. So I'm going to have the same free body diagram all the way to 4.99999. So those are my values of V, negative 10. Now here at 2, I get negative 20. At 4, I get negative 40. Well, guess what? You can do the calculation. At 3, I get negative 30. At 1, I get negative 10. And at 4.9999999, I would get, negative 50. Well, I would get negative 49.999999999, which is close enough to negative 50, so I'm going to call it negative 50. So for all of, we've been able to figure out all of the V's and M's from 0 to 4.9999999. Okay, so let's look at what happens when we do cut 3. Cut 3 is where? Cut 3 is over here past the roller. So what are we going to get for our V, N, and M? So now I have to include, what do I have to include? I got to include the 20 kips there. So when I do my cut 3, I'm going to have my V, N, and M over there. So what do? I take the sum of the forces in the y direction equals 0. Well, now I've got an extra force. I've got that 20. So I have what? I have minus 10 plus 20 minus V equals 0. I solve that for V, and I get 10 for V. Then I take the sum of the moments about point D. There's point D right there. And you can all do this. I'm going to have what? Negative 10 times 7, because it's counterclockwise. And then I'm going to have positive 20 times 2. And then, of course, this is counterclockwise, so it's minus M. So negative 10 times 7 plus 20 times 2 minus M equals 0. I get M is equal to minus 30 cubic feet. Now I can use either side of the cut, excuse me, but I have to be consistent. So, in other words, if I want to use, instead of, I make the cut, so there's my cut 3, instead of using this part of the beam, I can also, I can use this part of the beam and analyze it. That's fine as long as I'm consistent. Now here's where I say we have letters there, and so I set the directions. But if I'm going to do another free body diagram, I have to be consistent. So if I do this free body diagram here, I have to be consistent. They have to be consistent. So in a sense, it's a little bit, so I can't quite do what I said earlier, which is, well, if it's a letter, you can pick whatever direction. No. When you first get going, yes, you can pick whatever direction you want. But once you've set that up, then you've got to be consistent the rest of the way in solving the problem. So what do I mean by being consistent there? Well, that means that my V is down here, so my V has got to go up there. These are adjacent free body diagrams, and if you remember, they've got to be equal and opposite. So if one goes down, the other's got to go up. If this one goes to the right, that one's got to go to the left. So one goes to the right, one goes to the left. If this one is counterclockwise, then that one's got to be clockwise. So we have to be consistent there. And if I look at this free body diagram and I'm consistent and I've done everything, then what do I find? I get the same result. I get V equals 10, V equals 10. I get M equals minus 30, M equals minus 30. So just to let you know that if you use the other side of the free body diagram, you will get the same result. So when we go back to, so let's put those values into our table. At 7, I have 10 and negative 30. Well, I'm going to let you do the rest, but what you're going to find is the pattern, which is that all these values are 10. In other words, it doesn't matter, if I cut here, 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 wherever, I'm going to get positive 10 in that region. And then over here, we're going to find the reverse. So it's going to go negative 50, going to go negative 50, negative 40, negative 30, negative 20, negative 10, 0. So you can check those out yourself by making other cuts. So I now have all the values of x's, all the values of v, all the values of m. Now v is called the shear, m is called the moment. So what does that mean for us? I can plot these values up in this is the way we're going to do it. Here's my beam. here are my reactions. Here's my load. And we always do this in this manner. So I always line everything up in a vertical, and everything lines up. So I draw two graphs underneath here. Graph number 1, and like I say, this all lines up, is the shear diagram, shear. So I plot V, the shear. And graph number 2, like I say, it all lines up, is the moment. And now we are going to plot these values. So what we found was, at x equals 1, it's negative 10. At x equals 2, it's negative 10. At x equals 3, it's negative 10. At x equals 4, it's negative 10. I haven't quite done this one. At x equals 4.99999, it's negative 10. Up here, it's all positive 10. So when I plot this, what do? I got a line across there. I've got a line across there. Now I'm going to connect them. So I'm just going to go straight down. And it looks like that. So I have now plotted the shear diagram. And it looks like this. Okay. Then I plot the moment diagram. Well, what did I find? I find it's negative 10, negative 20, negative 30, negative 40, negative 50. Negative 40, negative 30, negative 20, negative 10, 0. Okay, so I had a 0 in there over there too. So I now can plot the moment diagram. And it's a straight line there and a straight line there. So I now have the moment diagram. Now, that was sort of a lot of work because we had made a lot of cuts. I'm going to show you a shortcut to do this, and we're going to use the shortcut that always works, and it makes sense, and you'll see why, and we will derive the equations. For the time being, I want you to, before I derive the equations, I want you to sort of accept it because we just verified that it works, and then we will derive the equations to illustrate that it does work. So, what are we going to do? Okay, so to draw the shear diagram, we're going to follow the arrows. So the key here is, for the shear diagram, we're going to follow the arrows. For the moment diagram, we're going to follow the areas. So arrows, areas. What do I mean by that? I've got arrows here. So we're going to begin at 0 and end at 0. So that's what I'm going to do. I'm going to follow those arrows. I start at 0. That says go down 10 kips. So I go down 10 kips. That's what the arrow says. There's nothing in this region. There's no forces in this region. That tells me I go straight across. Then I hit this arrow. That says to go up 20 kips. So I go up 20 kips. So in other words, I'm at negative 10. I'm going to end up at positive 10. So this whole thing is 20. So, and then there's nothing in this region. No forces, no arrows. So I go straight across. Then I hit that 10, it says go down 10. I end up at 0. So I started at 0, I ended at 0. And I followed the arrows. Down 10, over, up 20, over, down 10. Started at 0, ended at 0, and okay, now what I'm going to do is get the areas. So now I'm going to get the areas here. I'm going to get this area, I'm going to get that area. Well, that distance is 5 feet. That is negative 10 kips. So it's a rectangle. So that area is 5 feet times negative 10 is negative 50. This area is 5 feet times positive 10 is positive 50. So what I'm going to do, so I'm going to start at 0 for the moment diagram. And, I go from left to right, so I make sure I go left to right. So by the time I get to here, I'm going to be at negative 50. So I go like that. Now this is positive 50, so I'm at negative 50. I'm going left to right, so when I get to all of that area, I'm going left to right, I get all that area, I go up positive 50, I end up back at 0. So again, I started at 0, and I ended at 0. So in all of these cases, you've got to start and end at 0 for both of these, for both the shear diagram and the moment diagram. Now we're going to observe a couple other things here, and that is that what's the slope of this line? Well, if I figure out the slope of that line, it's negative. First of all, it's a negative slope, right? Negative 50, and it's over 10 feet, so the slope, or sorry, go over 5 feet, so the slope is negative 10. And if we, it's negative 50, notice the units here, negative 50 kip feet, negative 50 kip feet over 5 feet gives us a slope of negative 10 kips. And what do we note? Oh, everywhere in this area, that's negative 10, and the units are what? Kips. Kips. So the slope is negative 10 kips, and what do we see? The shear value is negative 10 kips. So the slope of the moment diagram is equal to the value of the shear diagram. The same thing occurs here. What's that slope? That slope, you can see, is a positive slope line. So that's going to be a positive 10. And oh, the shear is positive 10 kips. So again, we see that the slope of the moment diagram is the value of the shear diagram. Then, we've already verified that the value of the moment diagram is equal to the area of the shear diagram working left to right. So when I say, so I'm working left to right, I take that area is negative 50, so my moment, so I'm going working left to right, so that's got to be negative 50. Well, that area is positive 50, I'm working left to right, so I take this negative area there, add it to the positive area there, and I end up at 0. So you need to know a couple things. First, to get the shear diagram, we follow the arrows. For the moment diagram, we follow the areas. That's how you draw them. And then you need to know this other part of it, which is the slope of the moment diagram is equal to the value of the shear diagram. And the value of the moment diagram is equal to the area of the shear diagram working left to right. We're going to work a lot of problems, and so you're going to know this because we're going to do a lot of them. Okay, I'm going to stop there.